like carbon. How can one explain that? To explain that, they propose the shock wave. The shock wave imposes a huge pressure on the carbon elements and compresses them to form diamonds embedded inside a carbonaceous material, sputtering of carbon 60. Let me skip all these models. Not much time. How much time I have? Yeah, only 15 minutes. Let me come to few applications and close my talk. These energetic particles have been used by mankind in many, many different areas. They have been extensively used to characterize and modify materials. They very, very controlled with. Large number of important applications have emerged over the years. These include solid-state nuclear track detectors, microfiltering, hadron therapy, geochronological dating, engineering of nanomaterials, simulations of radiation stability, and of course, radiation environment in outer space. I will touch upon some of these aspects and then close. Historically, ion beam-based materials and started with solid-state nuclear track detectors. What are these? These track detectors are dielectric insulators exposed to cosmic rays or nuclear radiations from radioactive materials. When charged particles, high energy charged particles, penetrate through this uh, dielectric medium, they amorphize the track along their path, amorphize the medium along the path. We call it in tracks. So these tracks you are seeing, black lines, are nuclear tracks. These tracks have found applications in many areas. For detecting cosmic rays, okay, you take such nuclear, such dielectric matrix and expose it to cosmos. We are always exposed to cosmic rays of very highly energetic particles coming from the outer space, from cosmos, from sun. Okay, so these create tracks, detection of cosmic rays, detection of fission fragments. If one is doing some nuclear reactions, this can be used as detectors. Study of meteorites and lunar samples. Look at these tracks. These tracks have a lifetime, almost infinitely long lifetime. Once they are created, they stay there permanently. And hence, they can be used to determine the age of the material, how long the material has been there, just by counting the number of tracks. And hence, lunar samples, meteorites, archaeological age determination, geology, planetary sciences use these nuclear tracks. If you take these tracks and etch them by a chemical means, you will find that the surrounding crystalline region are left intact. They are not etched, but the amorphous matrix easily come out. You create holes. The dimension, nanometric dimension of tracks can increase up to micrometers. And it's a imagination is the limit to find applications of such techniques. If you do not etch out, if you just leave it, these tracks embedded in a superconducting matrix, insulating tracks, not non-superconducting tracks, embedded in insulating superconducting matrix, can be used to pin magnetic fluxes and enhance the critical current by orders of magnitude. You can dope, you can put p-type semiconductors from one side, n-type semiconductors from the other side, and in these holes, and create arrays of p-n junctions. Many such applications. Let me not go into that. Simulating outer space irradiation environment. Our outer space is a hostile environment. Many energetic particles are coming from sun and from many other stars, from explosions, stellar explosions and all kind of things. Many highly energetic particles. We call it cosmic rays coming out of them. Okay. When our spacecrafts, satellites are sent to the outer space, many electronic devices used in them, they are constantly exposed to these cosmic rays. Can they withstand these cosmic rays, these radiations, hostile environment? To test that, you don't send just to test whether a device will withstand, the outer space conditions, you don't send a satellite for that. That's like developing a medicine and directly trying it out on human beings. You don't do that. You try it out on smaller forms of life like rats, frogs, and then if you succeed, then you go to human beings. Similarly, we don't send satellites to test whether a device will sustain outer radiations. Rather, we take this device to an accelerator and subject it to same kind of radiations as coming from cosmos and with very high energy frequencies. So within a short time, we can find out if the device can sustain the outer radiations or not. Similar logic is used for radiation hardness of materials used in nuclear reactors. In nuclear reactors also, high energetic particles, alpha rays, neutrons, very charged particles come out. The devices used, the materials used there, not just electronic devices. Any material that is used, if it does not sustain, does not live against this hostile, strong radiations, it will collapse. If it collapses, then you have Chernobyl kind of disaster. Okay, so one shouldn't have that. To see, to test, to find out if a material sustains this kind of radiation environment, one takes it to an accelerator, exposes it to same kind of radiations and finds out, studies its property, finds out whether it's a resistance to amorphizing radiations, to volume swelling and all that. Well, the last applications I will talk and then I will stop. Hadron therapy. We are all familiar with treatment of cancer by X-rays for quite a long time. If there is a cancerous cells closer to the body surface, X-rays to some extent are useful. If the cancerous cell is buried deep under the body, if I take this zero as the surface of our body surface, and if cancerous cell, the tumor is buried deep, then X-rays is not very suitable. One thing is X-ray cannot penetrate deep into the body. And another thing is it destroys more healthy cells than it kills the cancerous cell. This dotted blue line, look at that. This is the amount of dose our cancerous cell get, but our healthy cells get much more dose. We don't want to destroy our healthy cell and instead of killing our tumor. But proton therapy, hadron therapy we call it, it's just a beautiful technique. It's a 100% efficient technique to target to the tumor. You can choose your ion energy such that, here I have given you a graph, this blue line, such that its maximum energy deposition is at a particular depth. We call this peak as Bragg peak. This occurs when ion travels at the same velocity as the electrons. There occurs the maximum energy deposition. So that one can easily choose by choosing the ion energy. Choose the ion energy such that your Bragg peak occurs at the tumor. So you see this orange line, you find that the tumor is exposed to the maximum radiation and healthy cells are not much exposed, very little exposure. The tumor is easily cleaned. Well, in conclusion, I would like to state that I do not have a conclusion. Why? Ion beam-based research is ever expanding, nourishing many other branches of science, not just material science, and providing unique application possibilities not achievable by any other means. So the secrets are still unfolding day after day, and hence no conclusion. Thank you all.
Thank you, sir, for giving us an overall idea about the modification of materials using ion beam and the important applications. It was truly a memorable talk and really a valuable contribution to our FDP webinar. We have some questions from the participants.
Yeah, I'll be happy to listen to those questions, yes.
So the first question is, what is the delta electron?
May I know the participant? If the participant directly asks, I'll be happy. Can they do that? Or otherwise,
So they're
Suparpita, you
putting their
can.
questions in the chat box. I'm reading
Fine,
out.
fine, fine. It's okay.
So they're sitting in the smart room and they're just putting their questions in the chat
Please,
box.
they can reveal. You can tell their name and the question.
Yes, sir. The first question is from Radhakanda, sir. He's asking, what is the delta electron?
Radhakanto from OUTR.
Yes.
If I remember, he was also my student in early days. But anyway, Radhakanta, I'm very happy that you have asked this question. Delta electron, let me slow this side. Can I? Yeah. Yeah. I told secondary electrons and delta electrons. Two kinds of electrons I am recognizing. As an ion travels, if an electron is directly hit, that electron comes out with tremendous energies from that region. We call them as delta electrons. But sometimes electron can get excited. One electron hits another electron. That electron, second electron comes out. We call them as secondary electrons. Yeah. Next question.
Next question is from Radhakanda, sir. He's asking, how do we get the coherence of electrons all along the path of ions, because there may be space charge defect?
Great, great. That's a very nice question. Yes. So should I show it here? No, here. Yeah. As I told you, as this ion travels inside with a velocity more than the velocity of electrons, so it pierces inside atoms. That picture I showed you in somewhere I showed you just in Coulomb explosion model. Yeah, here also. Its ion is piercing through the electron cloud. Okay. So what will happen? It's like a bullet passing through a series of footballs. It just makes a hole through all the atoms. Our ion makes a hole through all the atoms. So when it makes our projectile ion from the accelerator goes through all the atoms, all the electrons along the path simultaneously get excited. Okay. So electrons, these are, particles, negatively charged particles, they can equilibrate amongst themselves within a femtosecond time scale, and you get a coherent excitation together, all the electrons. Coherent means what? Simultaneously, all the electrons getting excited together. It's a many body problem, not a two-body problem, single particle excitation, as is in our this kind of process. This kind of process is elastic scattering is a two-body particle problem, but electronic excitation is a many particle problem. All the electrons are excited along the path. Yes.
So the next question is from Chittaranjan Biswal. He's asking, what is plasmon period? Chittaranjan Biswal.
Yeah, from which place?
I'm not sure.
And student,
I think
faculty,
student.
please do that.
I think student. I don't know.
Student.
He's not the faculty here, so I'm not sure.
Okay. No.
Okay. He's asking, what is plasmon period?
Yeah, that's right. You are familiar with the four states of matter: solid, liquid, gas, and plasma. The basic difference between plasma and gas is gas is a non-interacting system. You define ideal gas, non-interacting system. You can have two particle interactions. Same thing that I was trying to tell Radhakanta. Plasma, you have a many-body effect. Large number of electrons, ions coming together, they form a many-body system. Okay. And this plasma can oscillate at very high energies, plasma oscillations. Okay. That oscillation frequency is called plasma frequency. Plasmon period is inverse of that frequency. Okay. Oscillation of electron cloud against positively charged ions. Here, look at this figure. I have created high density of electrons. Ions are wherever they are there. This electron cloud can oscillate. It's a plasma, electron and ion together. This electron cloud can oscillate against this positively charged ion at a frequency called plasma frequency. inverse of that frequency, so plasma period. Yeah, next question.
Next question is from an integrated MSc student, sir. She's
Good.
asking, can you please tell the way of hadron therapy, which you've already explained, I think.
Can I tell?
The way of hadron therapy.
Yeah, what's her name?
Rupashri Datta.
Okay, Rupashri. I talked about it, but I am not an expert in this region. But I can tell you, can still tell you, hadron therapy is treating cancerous cell using hadrons. Hadrons, what are hadrons? Protons, neutrons are hadrons. So that's why it's called as hadron therapy. You can use even carbon particles also, high energetic carbon ions to treat cancerous cells. The principle is very simple. You shoot protons from left side. Left side is your body, your skin. Let's say this is a tumor inside our head, somewhere. I am shooting X-rays to kill this tumor, but X-rays instead will kill many of my healthy cells. But this proton can be targeted such that the maximum energy is deposited at the tumor and minimum energy, this orange lines, is deposited elsewhere. So healthy cells are not much affected. Only the tumor cell get all the doses from my radiation. And you kill the tumor, destroy the tumor. Yeah, next question.
Next question is from an MSc student, sir.
Name?
Abhinash Misra.
Yes, Avinash.
He's asking, is hydrogen bomb still a theory now, or is it being used practically?
It is already developed, and let's hope this Ukraine war doesn't take us in that direction. If that explodes, that is much more devastating than ordinary atom bombs. Let's hope that doesn't happen. Yeah, next question.
The next question is from an MSc student, Supriya Priyadarshini.
Supriya, yes.
She is asking, what is the radiation hardness test?
Yeah, this is, you just take a material, expose it to radiations coming from accelerators. If the material survives, it's hard. If it doesn't survive, it's gone, it's soft, it's damaged. And that's how you test radiation hardness. That's a very interesting question. The materials used in space applications, materials used in nuclear reactors should be radiation hard. They should sustain, they should survive very hostile radiations. They should be radiation hard. And that hardness you test using an accelerator, because accelerators can provide ions of different kind that's coming out from space, that's coming out from nuclear reactors, but more efficiently than these space and reactors, because the number of ions coming from space is very, very small. Now, from nuclear reactors also very small. But in an accelerator, you can create very high density, large number of such ions coming out and test the radiation hardness within a very short time. Yeah, next.
Next question is from D. Behra, sir.
Professor Behra, my student and professor. Great.
He's
very
asking, nice. H2S shows room temperature superconductor under high pressure of the order of million of atmospheric pressure,
yes,
gigapascal.
Yes.
Is it possible to freeze H2S gas and under shock wave, it will be room temperature superconductor?
Great question. Very nice question. This, what is that? Where did I talk about it? Just 1 second. What is that applications I talked about? No, model. I was talking about model. In that model I talked about high shock wave model. Yes, Professor Behra. In principle, yes. If this shock wave, high pressure, can compress carbon atoms to form a nano diamond, why can't it compress hydrogen sulfur to form a high pressure phase? but in practice, no. After once nano diamond forms, it's a crystalline phase diamond, it survives, it remains. But this hydrogen sulfide phase that you get superconductivity at about 15 degree Kelvin or so under high pressure, you get it only when it's permanently pressurized. That you cannot achieve after the passage of the ion. Ion passes, it creates pressure, but that pressure relaxes after the ion has gone through. So there is no other pressure, no pressure inside. So you will get that superconducting state only for fraction of a nanosecond perhaps, but then it will 1 second relax back to the ordinary hydrogen sulfur. You cannot get a superconducting phase embedded by this technique. Sorry for that. Okay.
Okay.
So the
Yeah.
next question is from Bobita Ojha, madam.
Uh-huh. Yes.
She's asking if proton therapy use energetic ions, then how the good cells in the human body are protected?
Yeah, that's how I'll show you. Babita, look at this orange diagram. They are not completely protected. They are subjected to less radiation. This orange line is little lower level. This line shows radiation dose. Maximum dose is at the proton as the tumor point. Their tumor gets damaged much faster. Ordinary cells do get damaged, but very little, not much. However, compare that with X-rays, this dotted blue line, that kills ordinary cell more, but doesn't affect the tumor cell much. Tumor is much less affected. Yeah, that's a very nice question. Next.
Next question is from Haripriya Rath, ma'am.
One second, student. Haripriya, yes?
She's asking, C60 is a cluster beam.
Yes.
Please explain irradiation with a single ion beam and cluster beam, how they are differing as per the thermal spike mechanism.
Okay. That would be a little more involved, but briefly I can try to tell you if I have a figure somewhere. Let's take this figure. That will be, this is a thin film. I can shoot with a single ion beam, let's say like 200 million electron volt iodine ion, or I can shoot cluster beam. Cluster beam carbon 60. Remember, I talked about through that hydro shock wave model that carbon 60 molecules can come out of the surface because of the shock wave. But what Haripriya is talking about is different. Shooting carbon beams, carbon 60 clusters from accelerator, it's possible. You can accelerate carbon 60 clusters to high energies, not million electron, that very high energies, but several tens of million electron volt you can accelerate, and these carbon clusters can penetrate through. You can calculate the energy, the AC of each carbon ion. There are 60 carbon ions penetrating. Add up the AC of all the 60 carbon ions and say that whatever one carbon ion energy deposits, the 60 carbon ion will just addition of that much of modifications. No, it's not that. There is a synergetic effect. When the cluster comes, it causes much more modification than just simply single ion carbon beams, 60 of them together. More than that, Haripriya, I cannot go that in this talk. It's a much more involved analysis. Thank you very much for this question. Next question.
So the next question and the last one is from our MSc student, Swaraj Patnaik.
Okay.
He's asking, by
Yes.
comparing the ion beam effect in asteroids and the experiments done here, can we get informations on the different type of cosmic radiations present out there in deep space?
Yes. So we'll close this talk with a beautiful question from Swaraj. Thanks a lot. Yes. one big difference between the radiation environment on asteroid and on our Earth surface is asteroid is in a very, very high vacuum, no air molecules surrounding it. But on the surface of the Earth, cosmic rays have to travel hundreds of kilometers of air, ionized surface, air medium to reach the Earth's surface. So in the process, many of the cosmic rays get attenuated, the energy gets attenuated. We don't get a true figure, true picture. Okay. In an asteroid, we are getting the nascent effect of cosmic rays, not unperturbed effect, because ions straight come and hit without getting perturbed, without getting attenuated by surrounding air medium. That's a big change, big difference. In fact, that is why we look at lunar samples, lunar surface, surface of the moon is also no atmosphere there. It's high vacuum. So cosmic rays effect there is very different from cosmic rays effect on Earth, where cosmic rays have to travel the deep atmospheric region. Yes, thank you very much. Anything else?
Like I already said, sir, it was truly a memorable talk for all of us. And on the department, behalf of the Department of Physics, I thank you, sir, for sharing your time and the research with us. Thank you, sir.
Thank you very much for giving me this opportunity.
Thank you, sir. Thank you, sir, very much for joining us. And we felt like sitting in our MSc classroom and asking questions to our faculty, respected Naresh sir, and got very good answers also.
Thank you, Babita. I have enjoyed much more interacting with all my students here.
And I request sir to please come for offline mode of presentation and interact with our students, because students, they are not able to interact directly with you. So
Anytime you ask me, I will be there in your college in offline mode to interact with the students. I like interacting with young minds.